Log on, tune in, find out. Another good idea from Cambridge.
Okay, well, Sandra intimated the reason I think I accepted to be a discussant of this session, and maybe the reason some of you are here in the room, is that I'd heard of step wedge designs, but I didn't know much about them, and this was a kind of opportunity to learn and do some reading. So you learn about topics by having to give a talk about them, by having a PhD student who works on them, things like that. So this was my opportunity to learn. So I'm very grateful to the previous two speakers for their material and inspiration about this. I find this a really interesting design. I think it's quite challenging, obviously, in terms of statistics, and certainly when you get into the kind of survival time to event outcomes of individuals, I think it's really challenging, and maybe one could agree with Larry's last conclusion, is actually quite dangerous in that context. But it obviously is also a useful design, especially in policy interventions. So where a policy is going to be implemented anyway, and it's a way of trying to do an evaluation at the same time as getting the policy gradually implemented. And so you get evidence out of something which otherwise you would gain no evidence about the effect of the intervention. So it can, I think, be very useful in policy terms. And as we've heard, and some of my comments, I'm afraid, will go over some of the things we've already heard, it's a kind of mixture of different designs. There's a crossover where you don't cross back. It's usually, I think, cluster randomised, although Celia talked about individuals potentially being randomised as well. And of course, it has this longitudinal aspect, which isn't always the case in conventional cluster randomised trials. So it is a mixture of all these things, and we've seen this diagram before, so I don't have to reiterate that. That is the basic design, where typically clusters will be randomised according to the rows they go into and time is going across. And gradually the whole cohort gets the intervention by the end. And I think one thing which hasn't perhaps been made totally clear so far is that you could look at the intervention effect in two ways in this diagram. You look at it vertically and compare, time-specific strata, and that's what Larry was doing exclusively, I think, and just say we're going to compare treatment and controls, and by doing it in slices, I'm going to control for secular trends. But you could also look at it horizontally, a bit more akin to what you do in a crossover trial, and say what happens when somebody changes from being, or cluster changes from being controlled to treatment, and using the other ones as a control. So you've got a controlled, randomized before-after comparison. So you've got actually both those comparisons, and in fact, you can do both of those simultaneously, or show a model where you do that. And just a note, when people draw these diagrams, typically, although I think Larry wasn't like this, you have the first slice, everybody's in control, and the last slice, everybody's in treatment. That's how they're typically drawn, and that gives no vertical information about the treatment effect, but of course it does contribute to the horizontal comparisons. So I wanted to just sort of compare how this stepped wedge design sort of contrasted with other things that might be slightly more familiar. So in the top right-hand corner, that button, yeah, this is I think the smallest step design you could call a step wedge. It's 2 by 3, okay? So that is step wedge, but it's a pretty small one. Now, if you just took the middle two periods of that, and you just have control versus treatment, so that would be a parallel group cluster randomized trial. To randomised to control or treatment. Those are obviously very plentiful. These are quite plentiful as well. So this is the first two periods from a step wedge design, is where you have a control period before you then randomise the clusters. And so this is a cluster randomised trial with baseline. And in my experience, although you could analyse that both vertically and horizontally, in my experience it's analysed vertically but making an adjustment for baseline. But you could do essentially the sort of analysis you might do for a step wedge designs. I think this is less common, where you have a sort of post-treatment allocation in everybody, but obviously it's essentially a rather similar situation to that from an analytical point of view. And that sort of contrasts with the sort of designs that Ian White was talking about on Monday, the cluster crossover trials. So that's where some clusters go from control to treatment, but other clusters go from treatment to control. And in that kind of trial, the analysis is typically done horizontally. In other words, comparing the cluster before or after it receives treatment. So it tends to be a horizontal comparison, or thought in that way, because that way you get rid of the cluster effects and you're comparing within cluster. This is also quite a common design. You have a crossover trial where you've got a baseline. And again, that would probably usually be analysed as a horizontal comparison with an adjustment for baseline. But again, there's sort of overlap between these kind of designs and the step wedge designs we've been talking about. So somebody was saying, do we really want a word? Are these, or we just have to explain what these designs are? And actually diagrams sometimes are the best way of explaining what these designs are. Maybe one word doesn't fit all. So the statistical advantages of a step wedge design are that the treatment effect can be estimated both horizontally and vertically, and that means both between clusters, that's vertically, and also within clusters, that's horizontally. Although Larry didn't do that because he's not using the horizontal comparison. So he's only estimating things vertically, and therefore it's not so efficient as other designs. But if you're prepared to make the horizontal comparison within clusters, then you may gain some efficiency, and that's because the intra-cluster variability, the effect of the ICC in reducing power, reducing precision, is going to be diminished because you're incorporating the horizontal comparison. And it has another advantage that you can investigate a duration effect, because some clusters will receive treatment for longer than others, and you can make that comparison. So there are some statistical advantages, and I'm not going to go into the practical advantages, disadvantages, because other people are much more experienced than me on that aspect. So this is the review which that Celia talked about, her review of 25 step wedge cluster randomised trials. And my conclusion from that, maybe from like a more statistical point of view, is that the statistical analysis plans were awful, actually. They were unclear, they were vague, they were inadequate. So, and somebody asked the question, even the ones that indicated they might be doing something which might plausibly be fairly reasonable, actually was it reasonable? Well, we don't even know. So yes, I mean, you would think that people using hierarchical multi-level modelling might be doing something reasonable. Somebody actually bothered to mention repeated measures. Well, that's encouraging. A couple of them mentioned G, so that's vaguely encouraged, but exactly what they did and whether it was appropriate, well, who knows. And that's 10 out of the 25, and it almost is only just bigger than the 9 who uses a very common method called not stated, which is very, very, very often used. And these sort of statements that we compared pre- and post-intervention periods using a t-test are completely hopeless. Although I think Celia tried to justify it at one point. So why is that? I mean, it's very obviously inadequate because we have to adjust clustering, we have to address the clustering, we have to address the repeated measures, we have to adjust the confounding by time through the cluster, through the experiment. And a simple comparison of the bottom triangle with the top triangle just failed to do any of that. Seriously inadequate. Some people do suggest that you could take this as the vertical slices step by step and do a sort of step-by-step assessment of the intervention effect through the period of the trial. And I think that's a useful kind of, I would treat it as an exploratory analysis, so to say how does that look as things pan out over time. But it's not giving you an overall assessment of the treatment effect. So I wanted to sort of try and write down what I thought might be a reasonable general model for how you might analyse a step wedge design. And I know this conference is about design and not about analysis, but to my view, you can't talk about design unless you also talk about analysis. Having a statistical analysis plan is part of the design of an experiment. And so I legitimise my focus here on analysis, and I'll come back to design just very briefly at the end. And there are different flavours of these kind of trials, and I'm going to look first of all just at a continuous measure, and I'm afraid there are some subscripts for individual I in cluster J at step K. Okay? And the first thing I'm going to think about is a cohort study, so you've got the same individuals being followed all the way through the trial without dropout and with a measure which is taken at the end of each step. So not a survival outcome, for example. So this could be phrased as a linear mixed model. So your outcome is some intercept term. You've got UJs, which refer to the random effects of cluster. You've got beta K, which refers to steps. There'll be typically fixed effects, which are trying to take out the secular trends of time. In a cohort study, you'd have a random effect for individual I within cluster J to take out individual level effects. That's a random effect. A treatment indicator T, so the theta is the parameter of interest, that's your treatment effect, you've got an error term. So in that sort of model, the fixed effects are theta, the treatment effect, the steps, the secular trend effects, and overall intercept, and the others might be taken as random effects and might typically be taken as normal random effects. And that strikes me as a sort of basic model that you could use. And if you look at that model in detail, the theta here is being estimated both horizontally and vertically, so that contributes the information of theta comes from both components in the design. And that you can easily adapt for other things. I looked at a continuous outcome, but there's no reason why you shouldn't just directly look at that as a binary outcome. You move from being a linear mixed model to being a generalized linear mixed model. So instead of modeling the outcomes directly, you model the underlying probabilities from a Bernoulli distribution with a logit link, and exactly the same model. So you can use exactly the same thing for a binary outcome as you could for a continuous outcome or analogous thing, and you could do the same for Poisson or whatever. And of course, if the trial is of a slightly different design, so that in fact you don't have clusters and it's individuals who are being randomized to the different steps, so you have step-weight individually randomized trial, then you just lose the terms which have anything to do with J. There's no cluster effect, and the individual effect has no subscript J. So it's a simplification of that model. I think the most common trial, maybe where this design is appropriate and might be used in practice, is the repeated cross-sectional design, where it's different people being looked at the different steps. I think it's probably a safer design in practice. And there's no individual variability, so you lose the I terms, but you have a cluster effect, but the model otherwise is similar. So that gives you a sort of a basic framework where I think you can estimate the overall treatment effect, and it allows also then extensions for what you might do. And people have talked about the effect of treatment duration. Well, instead of coding this as 0 and that as 1, which you would do normally, you can code this as 1, 2, 3, 4, depending on how long the intervention has been going, and replace the overall theta by something which recognizes that gradation. That's estimable from the data. There are other extensions which people who work in cluster randomized trials will recognize, that the cluster variability might not be homogeneous between the two treatment groups. That's something which has been talked about a lot in the literature. One also might make the other components of variability depend on whether you're in the treatment group or the control group. And there are many other things you could do. Modeling these things is quite complicated. In Ian White's talk on Monday, he essentially included a cluster period interaction term in these sort of models, which corresponds to a cluster time interaction in this type of model. So sort of borrowing from what you might do in a cluster crossover trial, you can argue that it would be important to include that extra random term. You could also include a random cluster treatment interaction. So there are all sorts of things you could do to make this model more complicated and explore, if you like, sensitivity of your results to different model choices. And my basic conclusion from this is these trials desperately need a proper statistical analysis plan. And to my way of thinking, this is not actually just words. It needs a model. And I think people should write down the model they are using. And you should write that down at the design stage. If you don't have a design, to me, unless you have that. So just briefly, analysis strategies. To my way of thinking, I look at this and I think, well, this is a hierarchical model, and hierarchical modeling seems to me the natural approach you would use. Yes, you can do things on cluster level models. So in other words, you summarize everything at the cluster level. It would be the cluster step, little box, if you like, and model that, and that might be especially good for sort of equally sized or equally precise clusters. You might get quite similar answers. You might try general estimating equations to take into account the clustering. But here you have got some potentially multiple levels of clustering, both the clusters, individuals within clusters, clustered by time interaction, might not be the best thing to do. It might be best to model those explicitly. And you might also be worried if you have small numbers of clusters, although Mike Campbell talked about adaptations of the G's which make modifications, which are good potentially in parallel group cluster randomized trials. Whether they'd work so well in step wedge designs, I think that's entirely open question. You probably expect me to say this, that I would regard quite a lot of advantages of a Bayesian approach, that it naturally propagates the uncertainty of the variance components you're estimating into the treatment effect uncertainty. If you want, you might be able to use informative PRAs for the interclass correlation coefficient, and it gives you a very flexible framework for the kind of extensions that you're talking about, which otherwise would be quite tricky maybe to compute in more classical approaches. Not impossible, but this gives you a very easy approach. So I'm not really going to talk about this, just to say this is now a slide that you can discuss if you want to, because there are a whole load of other issues. And just to sort of mention just a few of them. I think a lot of them have already been mentioned, actually. Missing data attrition. Attrition is going to be a clear problem if you're doing a cohort through time. Whether or not you've got a survival outcome, even if it's across anything where you've an outcome which is being measured in the same people, you could have differential attrition according to which group, how long it is before they get to the intervention. And missing data generally is going to be a problem. I think survival outcomes are particularly problematic, and we've heard some of the reasons for that in Larry's talk. And differential attrition, which comes about because of which intervention group you are in so far, is a clear example of how that might bias the results of such a study. Non-compliance we've heard mention of, and I think it'd be an interesting project for somebody to try and adapt the randomization-based non-compliance methods, which you use for an individually randomized trials, to the context of this kind of step-weight design. That's a very interesting PhD project. Contamination, lack of blinding, there's this typical problems which you might be worried about in these sort of designs. We haven't talked about adjusting for individual or cluster level covariates. We haven't talked about adjusting for baseline. We haven't talked much about model checking. So these are all things which I think would be issues which would need to be thought about, and Larry's given lots of examples of sort of model checking, or at least sort of sensitivity analyses which he's considering in his complex example. So my conclusions are that if you're planning one of these trials, amongst all the other things you have to consider is write down your statistical analysis plan, first of all in words, and then give the principle of statistical analysis model explicitly. That's, to my view, is part of the design. And you might mention your extensions and your sensitivity analysis you're going to do as well. And then you can base the design, and only when you've done this can you talk about what's the sensible design. Base this design and the power calculation on this principal statistical analysis model. Now, if you're lucky and you've got something that's nicely balanced and your clusters are equal sizes and your outcomes continuous and things like that, you might be able to do that analytically. And the paper by Hussey and Hughes gives an example where you can do that. You might be able to do that by approximation, and Larry gave an example of that where he had clusters of different sizes, and he said, well, let's use a harmonic mean as a summary of these different cluster sizes, which gives an approximation to what the eventual power might be. But if you can't do it by that, you do it by simulation from the model. You've got the model, let's simulate from the model, and you just do it again and again, you see what the power is, and you manipulate it. It's a bit computer intensive, but not half as much work spent on that as doing the trial eventually going to be done. So that would be my final conclusion. Thanks very much.
Thank you very much, Simon. We've got about 5 minutes, maybe a bit more for questions. Thanks.
I've got a comment, please. On your last slide, when I used to work at Rothamsted, trials had to be approved. And to be approved, you not only had to have a design, you had to have how we would analyse this, assuming that everything goes properly. I would have thought in the medical field it's even more important to have the thing approved in advance. So why don't you have to have a statistical analysis plan as part of what needs to be approved?
I think you should, and I think what we have at the moment is so it's papering over. It's like it's submerging what you're really going to do. So you have in your protocol, in your grant application, you have this little paragraph called statistical analysis.
And it says we're going to use ANOVA.
And it's 10 lines long. It says we're going to use ANOVA. Yeah, all going to use G's.
Whereas I used to have to actually provide a dummy analysis on fake data.
Yeah. I quite agree with you, actually. I agree with you in principle. Now you said, have I always done this for all the trials I'm involved in? Because I know that I've written statistical analysis plans, after the trial's been going for a while. I thought, my goodness me, how do you deal with this problem? How do you talk about this one? So, yeah, in principle, yes, but getting the practice there is another thing.
I don't think that we have as much problem with the protocol issue in the United States. I mean, there usually are very well thought out protocols The problem I find is the actual reporting in medical literature that you cannot figure out what they've done in this clinical trial. For instance, he just spent 20 minutes talking to us about a very sophisticated randomization procedure and showed me a medical article that has more than one sentence that says randomization was employed.
Why you would read when you can find one?
It's not necessarily the authors, the journal may say.
Yeah, the
"We're
journal.
only allowed
Yeah,
50 words on this. or
Luckily, there's
5
more
words
room
on
for
this."
online supplements these days, and that helps a little bit.
Yeah, and I think that's the important response. I think nowadays there's no reason for that because you can always have online supplements. And I think if sure you can't get detailed statistical models into your Lancet paper, but you can put supplements, and you should have these are supplements as long as you like. There's no excuse for it now.
I thought your model where you just wrote down the binary one was, didn't really incorporate Larry's model, which was survival analysis, because you could actually get TB while you're in the control group, and then you drop out of the risk set. So it's actually quite a different sort of analysis than the...
Absolutely. Absolutely. And I think, not only have you got the sort of problems of differential attrition and defining when people enter the risk set and things like that, but I think that's why, for example, you only look at the vertical comparisons. Because with a time to event outcome, you don't have a horizontal comparison to look at. So that's why you only look at the vertical outcomes in that context. But even if you do that, you've still got all sorts of problems, I think, of potential biases that might come into the results.
But we don't have the individual level of correlation because it's just happens or it doesn't. You can't express that variability.
But at a simple level, you have a time to event outcome. If somebody's had the event while they're still in the control phase, they then can't have the event in the treatment phase. And if clearly that can introduce a bias because the risk set is no longer comparable when you get to the treatment phase.
General question, but I wonder how people do view randomisation, permutation test sort of analysis. But thinking back to all the issues we were just talking about, my comments that would make this valid, but actually what you have to do then is say for each potential allocation of time that the intervention happens in each of those clinics, you've got to treat the whole data set as if that were the case. So the time that patients had a visit, not after the clinic actually got the intervention, but when it might have done if we said it was going to be then. So it's a very, you're repeating the whole analysis just with a simple, but the computers can do that. But I guess I suppose in the situation was that you do an intent to treat analysis or something that's as simple as possible, but it's not so great because there's a lot of noise due to treating people as if they've been treated when actually they haven't shown up the clinic. So if that didn't give you, if the intent to treat analysis didn't give you a positive result, and then your sophisticated model, which you knew might have brought in bias, did, it would be nice to have something to fall back on to say, well, here's something that doesn't have any bias in it. It's not, it's a different sort of analysis, but if that comes out the same way as your model-based analysis, that would be rather good, wouldn't it?
Yeah, they would handle one of about 20 different types of bias that are possible.
It's a limited, but I would say important technique.
Doesn't it handle every bias in principle? Because you're looking at all the hypothetical treatment levels that could have been there and doing the same thing each time.
Has anyone thought about potential outcomes sort of work in this area? Because there's all these biases around, a little like compliance issues in clinical trials. Have you thought about potential outcomes as a way to address that?
I don't know of any work on sort of the non-adherence or the non-compliance. Is that what we mean?
Just a sort of different approach to handle all these issues that are coming up.
We are going to have to wind up because there is a photograph outside that we're invited to. So let's just thank our three speakers first.